So I stated that the most important fact about the Smith chart is that it is printed on the complex gamma plane. More specifically, our contours, our mappings of constant impedance, resistance, and reactance map onto the validity region or valid region of the complex gamma plane inside the unit circle. That is the Smith chart. Yet, when we look at the Smith chart, there is an artifact, some things that are printed outside of the unit circle. We see that there is a ring around it, and on this ring we find three indices, three scales, three monotonically increasing values. And each of these three scales tell us something and help us use the Smith chart to solve problems. This outer scale is confusing to students sometimes in terms of how do we use them and what do they mean. So we want to go through and carefully look at the outer scale and try to understand what it is telling us. Again, there are three outer scales. The one we're going to look at first is the outer scale that is closest to the unit circle, that hugs the unit circle right along here. And if we look at that closely, and we were able to zoom in into one region of that scale, and we look closely, we see on a lot of Smith charts it'll say angle of reflection coefficient. And this is literally what that scale is. It is the phase angle of a complex value gamma. Remember, gamma, of course, is a complex number. It has a real part and it has an imaginary part, but likewise we can describe it in terms of its magnitude and its phase. In this case, the phase, like a polar plot, is the angle of rotation from the real axis, from the positive part of the real axis as we rotate along. Every point on the complex gamma plane has a magnitude associated with it. Let's say we have a point right about here. The magnitude of that point is simply the distance from that point to the origin of the complex gamma plane, to the center of the Smith chart. Well, what about the phase? Well, the phase is simply the rotation angle from the real part of the real axis rotation angle up to that point. How would we determine that angle? Well, we could take a straight edge and draw a line from the center of the Smith chart, the complex gamma plane, outward to that point, and then take a protractor and try to measure the resulting angle in between. But we don't have to do that with the Smith chart because of this outer scale. If we take a straight edge and draw a line from the center out through that point and continue it until it intersects this angle of reflection scale, we simply look at the number at the intersection of that line. In this case, if we look closely, we would find that number would be somewhere about 36 degrees or so. And that is the actual angle then of the reflection coefficient at the point located right about here. So we can take a point on the Smith chart, the complex gamma plane, and graphically we can determine the value of its phase by using this outer scale, striking a straight edge line from the center out through the point to the outer scale and measuring the angle to where it crosses, and that gives us the phase angle. Now, anytime we're talking about an angle around a circle, there's an ambiguity in terms of how we define it. We know that the circle will have 360 degrees or 2 pi radians, but where do we declare the angle 0 to be is one issue, and the other one is how do we describe the domain of that angle. In this case, for the outer scale, where we describe 0 is pretty simple. It's, again, how we define the angle with respect to the polar plot. It is the rotation angle from the the positive part of the real axis. And so a phase angle of 0 would be right about here. If we scale up, we can see right there it has a value of 0. Now, as we move in a counterclockwise direction along this angle of a reflection coefficient, we see that the angle is increasing. And we move up until we get this point, and of course then the angle is 90 degrees. As we continue along, we get to 130 and then 160, and then finally on the other side, we rotate all the way around to an angle of 180 degrees. Now, we could continue to rotate, and perhaps we might see an angle of 210, and then down to 270. But that's not the case. The way this scale is written on the on the Smith chart is as we move then from 0 in a clockwise direction, the values of the phase angle become negative. So we have negative 30, and then down to minus 90, and then up to, let's say, 150, and then finally we rotate around to minus 180 degrees. So in this case, the angle begins at this side of the Smith chart. Its smallest value is at minus 180 degrees, or minus pi radians, and it increases to minus 90 degrees, 0 degrees, increases still to plus 90, and to 180. And so that's how angle is defined on the outer scale of the Smith chart. And again, this gives us a way of taking a point, graphically taking a point on the Smith chart and having a method with a straight edge to determine the phase angle of that point without having to resort to a protractor to measure the angle between the line that intersects it and the real part of the, positive part of the real axis. All right, more specifically than just the value of magnitude and phase of an arbitrary point gamma. What we're interested in for the Smith chart is solving real problems with for terminated transmission lines. And in this case, the value of gamma, the reflection coefficient, will change as a function of index z, that position along the transmission line. And of course, we know that function to be the reflection coefficient function. Again, the transmission line is terminated, and it's terminated with some load reflection coefficient, gamma L. And in that case, the reflection coefficient function can specifically be written in this form. And of course, the thing that we know is the magnitude for lossless line will be a constant, independent of position z, index z, but the phase will be a change as we move up and down the line for a terminated transmission line. The phase of the reflection coefficient will vary in a way that's described by this equation. And it's fairly simple. It shows that the phase of the reflection coefficient is proportional to this index z, this location z. More specifically, it depends on the distance between the location on the transmission line and this purple ZL, which you recall is the numeric value at which the end of the line is located, where the load is attached to the very end of the transmission line. And again, that's an arbitrary value that we set up when we set up our original index for doing our problems. What are we going to call the end of the line where the load is attached? Oftentimes, that purple ZL will set as a value of 0 to simplify our maths, but I leave it as a variable for you to determine. So we're going to rewrite this expression a little bit, and we're going to take the value of beta, which remember is 2 pi over lambda. Beta is our spatial frequency, radians per meter. 2 pi radians for a distance in meters of lambda, for example, or 2 pi over 2 pi over lambda. Given the value of beta is 2 pi over lambda, we're going to rearrange this term and write the expression in this way, where we say 4 pi times z, index z, over lambda. Remember, z is an index, but it must have dimensions of length, some centimeters, meters, whatever. And we're going to go through and normalize that index by dividing it by lambda. By doing this, we make it into a coefficient, z over lambda. What we're doing is describing the index, the position along the transmission line, in wavelengths. And remember, wavelengths is the scale of microwave engineering. It's not how big something is, it's how big something is in comparison to one wavelength. And so that's the normalization that shows up sort of naturally in the mathematics here. The second term consists of two things that are important. The first, as we talked about, is this purple ZL, which is the index that we define with respect to locating the end of the transmission line where the load is. Again, we can set this to be whatever we want when we originally draw our index. Our transmission line cares not or knows not about our index. It's something we have to set up to be able to describe and solve problems mathematically. Oftentimes, again, it's ZL, and if you want to make it ZL, of course, this term disappears. What term doesn't disappear, however, is this theta L. And theta L, remember, is the phase angle of the load reflection coefficient. It depends on what's attached to the end of the line. And so from this, we can conclude that the angle of the reflection coefficient at a particular point in the line, an index Z, depends on the value of that index Z and depends on the thing attached to the end of the line, the load at the other end, gamma L. So from that, it tells us that we cannot determine the value of phase for gamma from simply the location of where we are on the line. We would likewise have to know what is attached to the other end of it. Say we're at some position on our terminated transmission line that's denoted by a index value of Z, and we get a resulting reflection coefficient and a resulting coefficient phase. Now we're going to move along the transmission line a distance of delta Z, and because we change our position, we change the value of the reflection coefficient. Not the magnitude, it stays constant, but the phase will change by some amount if we move along the transmission line a distance now of delta Z. What will the new phase be? Well, we can insert it into our equation and do some calculations, do a little algebra rather, and what we come up with is this result. The phase at some location Z plus delta Z is simply equal to the phase at our original location Z plus a value of 4 pi times delta Z over lambda. And so we have a situation now where the change in phi, the change in the, phase angle rather, the phase in the change angle due to a phase in our location along the line can be expressed simply now as 4 pi times delta Z over lambda, the change in distance normalized by lambda times 4 pi. Why is this interesting? Well, we'll see in a second why this is important. But one thing I will point out now is this change in phase with respect to a change in distance is independent now of the load that is attached to the end of the line. The fact that if we move some distance delta Z along the transmission line, we see that the phase will change, the reflection coefficient will change by a value of delta Z divided by lambda times 4 pi is true regardless of the load attached to it. So we can't determine the relative phase of gamma at any position on the line from just the position because we need to know what's attached on the other end of the line. However, we can determine what the change in phase will be for any transmission line due to a change in position regardless of the load that's attached to the end of that line. An example of this, let's say we move along our transmission line from one point to another, a distance of lambda over 4, 1/4 of whatever the wavelength happens to be. That's the distance that we travel along our transmission line. What is the difference in the phase of the reflection coefficient between when we began and when we ended by moving lambda over a distance of lambda over 4? Well, we can take our expression, simply take delta Z and divide it by lambda. That would give us a value of 1/4, and then we multiply it by 4 pi. And of course, then the change of phase would simply be pi radians. By moving the distance of lambda over 4 along our transmission line, the relative phase, the angle, I should say, of the reflection coefficient has changed by a value of exactly pi radians, or 180 degrees. We can express this again and show the same thing by doing just a little algebraic arrangement here. If delta z is lambda over 4, we can see that the normalized delta z, if we divide by lambda, is simply equal to 0.25. And given that we know the normalized delta z, we can insert it into the expression that we determined earlier, and we find that, again, the delta, the change in the phase angle of gamma from one point to the other, if a delta z over lambda is 0.25, is pi radians. And this is important from the Smith chart, that pi radians, of course, is a rotation of 180 degrees. We've rotated around the Smith chart exactly 180 degrees if we move a distance that is 1/4 of a wavelength. And of course, this was a special case that we talked about. Likewise, if we were to go through and change along the transmission line a distance delta z over lambda, which is equal to 0.5, 1/2 lambda, in that case the change in phase angle would be 2 pi radians, or 360 degrees. We simply rotate all the way around the Smith chart and come back to where we started. And this again was a special case. If we have a length of transmission or a distance that we move of exactly 1/2 lambda, then we are back to where we were in the Smith chart. We have exactly the same reflection coefficient as what we had at the earlier point. Remember, the reflection coefficient function is periodic with respect to lambda over 2. Why are we talking about this? Well, the key thing in all these cases is all these things are true regardless of the load reflection coefficient. Again, from the standpoint of determining the reflection coefficient angle theta using the location on a transmission line, we can't make a direct mapping unless we know what's terminating the transmission line. But we can know the change in that angle as we move up and down the line from one point to the other. And it turns out the change of that angle is what we really are going to need to know with respect to solving transmission line problems with the Smith chart. So I've talked a great deal about the relationship between the location of the transmission line z, the normalized index z divided by lambda, and the angle of the reflection coefficient function at that point. We've shown explicitly the relationship between those two things. Hopefully that was fairly obvious. We certainly have talked about that before. But the reason I wanted to go over that again is make sure that that's fresh in your mind when we start talking about one of the other scales, I should say, on the outer scale of the Smith chart. If we look closely in this region right over here of the Smith chart on the outer scale, oftentimes the Smith chart will have a term that says wavelengths toward load. There's, on this scale, 2 indexes, one on the very outside and then one on the inside of the scale. And we're going to look at the one on the inside first, the one that's denoted as wavelengths toward load. If we look closely, we find that the value of that index is 0 here, where the reflection coefficient phase angle is 180 degrees or minus 180 degrees, however you look at it, minus 180 degrees. Let's look at it that way. And as we increase the reflection coefficient phase angle from minus 180 to 170 to 160, what we find is that the scale here, wavelengths toward load, will likewise increase. It starts at a value of 0 and then moves to 0.04 and 0.05, for example. And it continues to increase as we move along this scale. Increases to a value at this location where the reflection coefficient phase angle is equal to 0. In that case, that scale, the wavelengths toward load scale, is at 0.25. And then finally, we move around to the end over here, and we find the scale converges to a value of 0.5. Well, we start at 0. When we're halfway around, we're at 0.25. When we go further around, we're at 0.5. This would indicate, and you might suspect, that this is a scale associated with the normalized distance along a transmission line. If we move a distance of 0.25, we know we rotate 180 degrees, which is why that scale starts at 0 and then moves to 0.25 on the other side. Or if we continue to rotate around from 0.25 to 0.5, we rotate another 180 degrees. And this is exactly what would happen if we move a half wavelength along our transmission line. We would rotate rather 180 degrees around our Smith chart. So the speculation would be that this scale is a normalized distance along a transmission line. And in fact, that is the case. That's what this scale tells us. It is a scale that is a normalized distance as we move along the line, which is why as we go from 0 back to 0.5, we rotate 180 degrees, or 360 degrees rather, around the Smith chart, because we have progressed a distance of a half wavelength along our transmission line. So that outer scale in the direction toward the load is a normalized distance along the transmission line. And this is the important point, and why I've tried to put the pieces together to lead to this point, in that oftentimes students conclude, because this is a normalized distance, it is the normalized distance of z divided by lambda. It is the index that we use to describe the location on our transmission line divided by lambda. And that is not the case. It is a normalized index, but it is not the normalized index that you will use to solve your transmission line problems. Instead of z over lambda, we could think of this index around the outer scale, let's just call it y over lambda, give it a different name, because in fact it is a different value, a different position index than the one that we use to solve our transmission line problems. So, assuming that we have defined and indexed z for a transmission line problem, such that z is increasing as we move to the load, we find that this index y on our outer scale that we're discussing now has that same property, that as y increase, we're moving toward the load, and that's why the transmission line says distance toward the load, or denoted that way. It is the same, the scale's the same, y and z, in that the distance between the end of the line where the load is to the beginning of the line, the difference between those two indexes must be equal to the line length L. And that's true both for the index y and the index z. So they seem very similar. Where they become different is in terms of the locations that are defined as z is equal to 0 and y is equal to 0. On one scale, the one that we defined, perhaps we set z is equal to 0 to be the halfway point between the beginning of the line and the end of the line. Or perhaps we set 0 to be at the very end of the line, and we'll call it zl. It doesn't matter. What we'll find is for the corresponding index y is the location of 0 will almost always certainly be different in terms of its physical location. Again, the numeric value y will indicate a different value on the transmission line than will the numeric value 0 for the index z. And that's why these two indexes are different from each other. You might be thinking, why are we making this so confusing? Why would the Smith chart manufacturer define an index y for the outer scale, which is different than this one that we would use to solve transmission line problems, where we use index z? Well, this is where I want to go back and talk about the math that we discussed earlier, and that's why I reviewed it again. This is the expression for the phase of the reflection coefficient function as a function of position z, our index z, in this case the normalized index z, when divided by lambda. And of course, if we evaluate this at specifically the index z is equal to 0, we find the value of the reflection coefficient phase angle at z is equal to 0 is given by this expression, theta L minus 4 pi ZL over lambda. In other words, the value of the angle at z is equal to 0, the phase angle at z is equal to 0, depends both on how we set up our index, originally ZL, purple ZL, how we define the end line, but more importantly also on the load reflection coefficient. And of course, this is why the Smith chart manufacturers couldn't put an outer scale which matched to the index that we use for our transmission line, is because, of course, the Smith chart manufacturers have no idea what the load at the end of your transmission line is. All the problems that we solve, generally speaking, will have a different value of load at the end of the transmission line. By placing a load there, we will change the value of the reflection coefficient function phase at z is equal to 0. The reason that the Smith chart scale, outer scale, y over lambda, can't be matched to the index that we use, z over lambda, is because you can't match them unless you know what the specific load is. And of course, the beauty of the Smith chart is allows us to solve problems regardless of the load at the end of the transmission line. In contrast, if we look at the reflection coefficient function and relate it to the y scale, the normalized scale on the outer ring of the Smith chart, we find the relationship between the gamma, the phase angle of gamma, and that value of y is expressed with this equation. And notice nowhere in there does it say anything about the load reflection coefficient. Again, it has to be independent of what the load reflection is, because it has to be valid for any and all loads attached to the end of our line. If we take this expression and we evaluate it at y is equal to 0, then we get a result which is equal to minus pi radians. And remember, we talked about this at the beginning. We go over to the the point on the outer scale here where the y, where that scale began at 0, and it increased as we rotated around. Well, this point over here, where the short circuit is, that had a phase of minus pi and became more positive as we rotated around. The key thing, again, is this relationship that we have depends neither on the load reflection coefficient, again, the Smith chart has no idea what that is, nor on the index that is used arbitrarily to set the value of y is equal to 0. If we look then at the outer scale on again at this scale next to the unit circle, that is the reflection coefficient angle. And then the other scale we're talking about now, this quote-unquote y scale, is given here. And we can see there's a one-to-one mapping for every angle, phase angle, 90 degrees, for example, it maps onto an index, in this case 0.375, that's given here. And this mapping between theta and y over lambda can be written in this form, where we map the phase angle of gamma onto y over lambda, or in this form, where we relate the normalized index y over lambda to the resulting value of theta. The reason I point this out and try to make this explicit is there is a definite, unambiguous mapping between y over lambda and the phase angle of gamma on the Smith chart. Oftentimes, students take this mapping to be an unambiguous mapping between the reflection coefficient theta and the index z over lambda, the normalized z over lambda. They think the Smith chart will be able to tell them where they are on the transmission line of their problem if they know what the angle of the load reflection coefficient is at that point. Or they think that if they know where they are on a transmission line, z over lambda, they can take that value and that value alone to determine what the reflection coefficient value should be at that point. But that's not the case, because again, we need to know what is terminating our line before we can make that determination, before we can relate one to the other. Yes, the Smith chart seems to make an unambiguous relationship between normalized position and reflection coefficient angle. But again, that is not z over lambda. It's an arbitrary mapping between the two that is given here. So just to complete description between mapping of our index y over lambda to the reflection coefficient angle. If we have a situation where y over lambda is equal to 0, the reflection coefficient angle will be minus pi, or minus 180 degrees. On the other extent, if we have a reflection coefficient angle of 180 degrees, that corresponds to a index y over lambda normalized index of 0.5. And again, we talked about this as we start at a minus 90 or a minus 180 degrees, and we rotate around the Smith chart back to plus 180. What that index will do is start at 0, go to 0.25, and then continue over to 0.5. And so as we go from minus pi to plus pi, our index will go from 0 to 0.5. And of course, 0.5 lambda is the distance around the complex gamma plane. This just shows graphically what I just said. We're looking again at this index wavelengths toward load. We start at 0, and that's the minus 180 point, or minus pi radians, and we move in this direction, and the wavelengths toward load will increase. We rotate all the way around the Smith chart, and as we come back in, we approach that value, goes to 0.47, 0.48, 0.49, and then finally 0.5, as the angle then increases to a value of 180 degrees, or pi radians. So the question is, what is the purpose of this outer scale, this normalized index that we have? How does it help us? If we can't directly map the reflection coefficient angle into a location on the transmission line, or a location on the transmission line back to that value unambiguously, why even put that angle or that scale on the Smith chart? Well, how is it helpful to us at all? Well, it turns out that outer scale is very useful to us. And again, it gets back to something I alluded before, in that in transmission line problems, it's not so much the phase of the reflection coefficient where you are, or the phase of the reflection coefficient at some other location. It is the difference in the phase between one location and the other. It's how the phase changes as a function of position, or more specifically, how far do we move to get our reflection coefficient to change a certain value. And in that case, for those problems, this outer scale is very useful. So the analogy that I use here for this outer scale, this normalized distance, is one where I compare it to mile markers that I'm sure you're familiar with along the interstate highway system. Here in Kansas, we have I-70 that runs across the state from east to west, or west to east, depending how you look at it. The mile markers along those lines that you see begin at the western edge, where the boundary between Kansas and Colorado, and increase as we move eastwardly. And of course, every mile, index increases by a value of 1. When we get to the very eastern end of I-70, at the border between Kansas and Missouri, the mile marker is 423 miles. Of course, that denotes the fact that that marker is 423 miles from the first mile marker, 423 miles from the other border. It takes 423 miles of driving to get from the western edge of Kansas to the eastern. So a little geography lesson. If we were to drive along I-70, along Kansas, as we progressed from west to east, we would pass by a number of towns, and each of those towns would have a mile marker associated with them, or at least their exit. Oakley at 76, Junction City at 296, Lawrence at 388, for example. What is the significance of this number? The fact that Lawrence is at 388, for example. Well, that means that we're 388 miles away from the western border, to be sure. But we didn't really have to start our index at 1 at that western border. We could have added 150, 125 to that value, and have the first index there be 125, and therefore the index at Lawrence would be 413 or something like that in that case. Again, the number's pretty arbitrary. It really doesn't mean very much. by itself. So how do we use these mile markers? Why are they put alongside of the interstates? Say you're traveling eastbound along I-70 and you're trying to get to Topeka and you want to know the distance, how much further you have to drive to get to Topeka. Topeka is a mile marker 361. Again, that by itself is really of no significance. It means it's 361 miles from the western border, but you're not at the western border. You're somewhere in Kansas. And so we want to know how much further do we need to drive to get to Topeka. You happen to look at the mile marker and where you are, and you notice it's at mile marker 184. Well, 184 is the mile marker that happens to be at Russell, Kansas. And so you happen to be driving by Russell at this point. To determine the value, the distance to Topeka from Russell, from where you are, you simply subtract the difference between the mile marker at Topeka, 361, and the mile marker at Russell, 184, and that would give you a distance of 177 miles. Again, 361 and 184 aren't any significance, but the difference between them two is the distance between you and Topeka, Kansas. Or if you are at Russell and you know that you need to drive, Topeka is another 177 miles further down the road, then you know you could add 177 to 184 and know that you need to drive until you get to the mile marker 361. So let's say you're in Lawrence and you look at the mile marker there and it's 388. And so you go through and take the mile marker for Topeka, which is 361. You subtract 388, the mile marker for Lawrence, and you get minus 27 miles, a negative distance to Topeka. What does that mean? Well, like so many things in engineering and mathematics, the positive and negative map to a direction. Because the mile markers are increasing as we move east to west across the state of Kansas, if I take a difference between where you are and where I want to be, and the value is positive, that means you need to move that much further eastwardly on I-70. But if you take the difference between the mile marker where you are and where you want to be, and it is, where you want to be and where you are, and it turns out it is negative, what it is saying is you need to move that distance now back westwardly in the opposite direction of the increasing mile markers. And so hopefully you can start to see here the analogy we're doing between mile markers and the index along the transmission line. There's a direction of increasing z as we move down toward the load, and a direction of decreasing z as we move away from the load. Just like the mile markers on an interstate, in this case Kansas, we find the mile marker direction of increasing mile markers as we move east to west, and a direction of decreasing miles markers as we move west to east. I should have done that differently. I realized by not thinking in terms of mirror image, but that made sense from my perspective. An example that hopefully is fairly obvious to you then. Let's say we're at Salina at a mile marker 251, we're trying to get to Salina at mile marker 251. And let's say we are located at Oakley, which is a mile marker 175. We take 251, where Salina is, subtract the Oakley mile marker of 76, and we get a plus 175. That means Salina is 175 miles east of Oakley. We need to continue down I-70 in the east direction for 75 miles to get to Oakley. Or on the other hand, let's say we're in Junction City, which is mile marker of 296. We take Salina's mile marker 251, subtract 296 from it, and we get a value of minus 45. This tells us that we need to travel 45 miles in the westerly direction to get to Salina. Or another way of looking at this is if we are at Oakley and we travel 175 miles toward the east, we'll be at mile marker 251. Or if we are at Junction City and we travel 45 miles to the west, then we will be at mile marker 251 as well. So hopefully all that was fairly obvious and straightforward, and you may be wondering why we spent time trying to explain it. It was so obvious. But like any good analogy that helps students understand a more complex problem, if you can see how simple and fundamental that problem is, and then you map it into something that may be a little bit less obvious to you at first, you realize it really is the same thing, and it's just as simple and it's just as obvious as the case of mile markers across Kansas in this analogy. Because that outer scale that we talked about, the y over lambda outer scale, the wavelengths toward load outer scale around the Smith chart, is really just like our mile markers. We can think of the value of 0 being mile marker 0, and then mile marker lambda over 8, lambda over 4, 3 lambda over 8, and then all the way back to lambda over 2. Of course, one difference between the Smith chart and the Kansas interstate analogy is if we travel from one end all the way to the other, we're back to where we began on the Smith chart, since our path is, of course, circular around that Smith chart. Recall earlier we showed that the change in the phase angle of gamma due to change of some distance along a transmission line can be written in this simple expression. And the important point about this expression is it is independent of the load of the transmission line. It is independent of gamma L. Again, we can't map directly the position on our transmission line Z to a reflection coefficient angle theta gamma unless we know the load reflection coefficient as well. But we can determine the change in that load reflection coefficient due to a change in location along the line without knowledge of the load terminating the end of the line. What we're going to find is that's true likewise for this scale value, again I call y over lambda, the scale value associated with the Smith chart. Just quickly here, if I were to go through evaluate this angle at some value we'll call y sub a, we get an angle of theta a. So let's move a distance delta y down our transmission line to a new location we'll call y sub b, and we'll evaluate the reflection coefficient there based on our mapping between y and theta, and we get this result here. Notice we have the original value of theta plus 4 pi times delta y over lambda, and this should look familiar to you. And so we can conclude that the change in the phase angle of gamma by moving some normalized distance delta y is going to be the same as the phase change in phase of the reflection coefficient if we move the same distance of normalized delta z. In other words, we find that delta z over lambda is equal to delta y over lambda, that if we normalize both to lambda, the values are the same, and we can use then either delta y or delta z to determine the change in the phase angle of gamma as we move along the line. And again, that is what is going to be most important to us with respect to transmission line Smith chart problem solving. This equation then summarizes what we've determined, that the change in the phase angle of gamma as we move along the line can be determined by using this outer scale of the Smith chart, this delta y over lambda, and it will give us exactly the same result as if we were to change the same distance along the scale that we use to solve our transmission line problems. If this value is what's really important, or correspondingly the delta is what's really important, then we don't need to have a scale that is exactly matching the transmission line scale Z. In other words, we don't have to know the load reflection coefficient to determine that change in phase or that change in distance. And so this is just analogous again to our transmission or our interstate mile marker problem. If two towns are 25 miles away, the difference between the 2 mile markers there is going to be 25 miles. Whether 1 mile marker is 10 and 35, the other one 35, or 1 mile marker is 150 and the other mile marker is 175, or whether 1 mile marker is 300 and the other mile marker is 325, none of that makes any difference as long as the distance between them, the difference between the two, is equal to the 25-mile distance between them.